Good evening, greetings and salutations, everybody, and welcome to the final content webinar number 88, which is all about cosmology. The examiners aren't too keen on asking about cosmology and galaxies for some reason on paper two, but I think they've been kind of nudged into producing some more questions. And certainly there was a nice, accessible one last year that I've included in this. So let's have a look. Three topics today. We've got redshift, the concept of redshift that we've seen before. We've got Hubble's law. Hubble features a lot in cosmology. We've already seen how Hubble classified galaxies, and we'll be meeting him again. And the Big Bang, evidence for the Big Bang, evidence that doesn't support the steady state or the cyclic theory. We're going to be looking at some quite highbrow stuff in astrophysics. So let's get on with it. So they're all examined on paper two. You wouldn't get any of this on paper one. Having said that, last year, the formation of the moon was on paper one, whereas it shouldn't have been. So occasionally, I don't know how this happens, occasionally we just get odd little hiccups. Right, the concept of redshift. I looked at this carefully today and thought, do we need to change this a little bit? Because I've just noticed, or I noticed earlier, that the scale isn't linear. We've got a big gap between 400. Presumably, this is wavelength in nanometers. So we've got a big gap between 400 and 500, and then less of a gap between 500 and 600 and 700. Can you see there's definitely a notable gap there? However, let's just ignore that. We've got some images of a spectra from looking back at the bottom, going up, a nearby star, a relatively nearby galaxy, not in the local group, but never mind, fairly close anyway, a distant galaxy, and a very distant galaxy like a quasar. And if you pick out certain lines here, you will find that they have been shifted compared with the star in our galaxy that I think we can assume is pretty stationary with regards its movement away from us or towards us. All the lines have been redshifted. Look at that band, that blue band. That's presumably due to, well, I don't know what it is. It can't be due to molecules because they would be in the red and the infrared cooler stars. I'm not quite sure what that dark black band is on the left-hand side. But look how much it's been shifted for the quasar. Wow. So we've got red shift. So the light that astronomers receive from distant galaxies is all red shifted. So there is a descriptive term, red shift. There's also a quantity as well. We'll look at that shortly. So it says, note that the spectral lines are shifted more and more to the red end of the visible spectrum for nearby galaxies. Distant galaxies, a larger redshift, and a very large redshift for very distant galaxies. Those that we can hardly see in the little sort of graphics that they've put in this on the left-hand side. And this was discovered in around the 1920s, 1930s, when he and his assistants had access to the world's largest optical telescopes. And he was interested, in different elements in the stars and the galaxies. But what he didn't expect was this redshift, which was so large. And we can interpret it in terms of something that, again, we looked at last time, the Doppler effect. We tend to hear the Doppler effect rather than see it. We've got our trusted pedestrian, well, let's call it a lollipop lady. I know we shouldn't call them that anymore, but I'm sure lollipop lady is what everybody knows. I don't know what the PC name is anymore, and I'm not particularly interested. We've got an ambulance approaching, and the notes have a higher pitch, as you can see, than the ambulance that's moving away on the right. So we get this change in pitch, a change in the perceived frequency, and it's all because there's a change in the wavelength of the light. or if you like, in this case, the sound. If a source of waves is moving away from us, it stretches out the wavelength. And if a source of waves is moving towards us, it squashes the wavelength. Now, like Hubble, you would probably expect some galaxies to have a bit of redshift as they sort of came towards us a little bit, and some blue shift. But there was no blue shift, apart from some very local galaxies like Andromeda. All redshift. And the funny thing is, he noticed that the further away a galaxy was, the faster it was moving. Well, the only way that he could interpret this is that the universe, and therefore particles in it, galaxies, are, well, the universe is expanding, getting bigger. Now, as well as a descriptive term, there's a quantity called redshift, which has a symbol Z. And it's the wavelength received, lambda, take away lambda naught, which is the measured wavelength, compared with lambda naught, and that, funnily, from the Doppler effect equations, which is A-level physics and beyond, which we're not going to look at today, is V over C. So the redshift, you could write this actually as delta lambda, the change in wavelength, over lambda, the true wavelength, is V over C. So you can see different versions of this. I think this is the one given in the formula booklet, but I don't think it has the Z equals. Just got lambda, take away lambda naught, so that's the shift in wavelength, over divided by lambda naught, the true wavelength, and that's equal to V over C, which is the speed of the galaxy divided by the speed of light. So V over C is actually a fraction. Z is a fraction. And it's the fraction compared with the speed of light at which the galaxy is moving away from us. The speed of light, you'll be given on the question paper, 300,000 kilometers per second. Pretty fast. 3 times 10 to the 5 kilometers per second, or 3 times 10 to the 8 meters per second, which we don't tend to use. We don't think in terms of, meters per second, the speed of trolleys in the physics lab and things like that. Right, so I've thrown in a worked example because we haven't got many of these from the exam papers. And astronomy uses the K line of calcium. So that's one of the spectral lines. They're given different letters and Greek letters sometimes. Don't worry about that. In the spectrum of light from a distant galaxy to determine its velocity. The rest wavelength, so the true wavelength, so this can be measured in the lab where everything is nice and steady and stationary and not moving at high speeds, is 393 nanometers. So it's in the definite violet region of the spectrum, down at the short wavelength end. If the measured wavelength in the spectrum of the galaxy is 454 nanometers, calculate the radial velocity of the galaxy. That's what it's called, the radial velocity. These velocities are all in the line of sight. And there we've got C, the speed of light, as 300,000 meters per second. Right. So what we've got to do is to use the formula. Lambda take away lambda naught, over lambda naught is V over C. The difficulty I think people have at GCSE is which lambda is which wavelength is which. So the true wavelength is lambda naught. The measured wavelength is lambda. So if you sub into the equation, 454 nanometers take away 393 nanometers divided by 393 nanometers gives you 0.1552 and lots of other digits as well. Don't write all those down, just keep them in your calculator. So now all we have to do is multiply that fraction, realizing it's V over C. So V becomes C times that Z, the redshift. And then we can do a bit of correcting, 46,600 kilometers per second. There we are. That's fast. 46,600 kilometers in a second. And that's in the line of sight away from us. This is typical of some of the distant galaxies that we have. On backwards, I think. Oh no, here's another one. One for you to do. If you've time, there we go. Just have a quick look at that. So 519, take away 396, all over 396, multiply by the speed of light. Once you get your eye in with these, and there's lots of examples on the math skills resource. I think you've all got that, haven't you? The answer you should get is 93,200 kilometers per second.
Everybody
That's
concur with that? Oh, I think things have gone quiet in chat there, Nigel. So
we might not have
that,
had we might not have had calculators handy, so not to worry. If you jot the answer down, guys, then you can check that later. Right, here's one where we are shown the spectral lines and we've got to estimate what their values are. Now, the distant galaxy is X, and the normal galaxy, the light from the lines in the lab, is Y. So spectral lines in Y have been shifted to longer wavelengths in the spectrum of X. And we've got, again, to estimate the recession velocity of the galaxy. Same technique, but we've got to estimate. And it does say estimate, so you wouldn't really need to have, millimeter accuracy in measuring. I reckon that dark line, the one darker than the others, in spectrum X is just over 500. Let's call it 550. I don't know what the answer says. We'll have a look in a minute. Nanometers. The other one is a pretty good bet, 610 nanometers. So it would be 555. Is that what I said? No, 655. Take away 610, divided by 610 times the speed of light. And if you do that, you should get something around 25,000 kilometers. There would be quite a nice little bit of leeway. So there we've got to use a grid, which is, well, not a grid, a chart with not a very precise, not a very, what's the word, sensitive scale there, just to the nearest hundreds of nanometers. Traditionally, astronomers use nanometers. They used to use things called angstrom units, and they seem to have gone out of fashion a little bit with this emphasis now on everything must be kind of metric and, adhere to the SI. So what Hubble found when he plotted the data, and he didn't have anything like the data we have today, and yet we do confer what Hubble found out. The further away a galaxy, the greater its redshift, and therefore the faster it was moving. And he plotted the results on a graph. So he got his velocity from the Doppler effect formula and the redshift measurements. He got his distance from observations of supernovas, and he found a lovely straight line through the origin. Physicists love straight lines through the origin. We get them a lot. And this shows that V is directly proportional to D. He was even so confident it's known as not just a principle of physics, a law of physics carved in stone. V equals H naught D. H naught is the Hubble constant. And it sounds a little bit strange, but over the years it has changed its value a little bit. So people say, well, how can it be constant? Well, we've refined it. We've got better and better methods at more accurately determining the value of Hubble's constant. Why there's a naught there, I am not sure. Perhaps somebody could fill me in on that, though I'm not particularly interested. V equals h naught d. The velocity is this constant, Hubble's constant, times the distance. And normally it's conventional to plot V in kilometers per second, because that's the unit that we've been using in our 3 calculations where we've had to calculate V. And D is normally given not in parsecs, definitely not in light years. Parsecs, no. Astronomical units, no. Megaparsecs probably is the distance. So Hubble's constant comes out in kilometers per second, slight pause, per megaparsec. 68 kilometers per second, pause, per megaparsec. In other words, if a galaxy is a megaparsec away, it will have a recession velocity of 68 kilometers per second. If it's 5 megaparsecs away, it'll have a recession velocity 5 times 68 kilometers per second. And Hubble trying to explain this with rising cakes and loaves of bread and balloons with ladybirds on. I don't think he used that one. I think it was more for a cake, I think. He suggested that because it appears that the galaxies are all moving away from us, and the further away the galaxies are, the faster they're moving, then it all started in a much smaller region of the universe, but the expansion is basically space, and it drags the galaxies with it. So the ladybirds here are representing the kind of plums and raisins and cherries that you might make in a fruitcake. Yeah, all getting further apart. So as the universe expands, it carries on, it carries along the matter in the universe. So the galaxies aren't receding of their own accord. They're being made to recede because they're in this, I know it's a vacuum, I know it's space, but this space is expanding. If you think it's complicated, it is. We're in relativistic physics here, and not the normal kind of world of Ohm's law and trolleys and conservation of momentum and energy of particles, kinetic energy, and so on. We're in really weird physics here. So don't try to go too deeply into it. You can do that after GCSE. That'll be a good little project to do. Teach yourself about cosmology. Oops. Wrong button there. There we go. So there we are, just reminding you again, kilometers per second and megaparsec. The interesting thing is we've got kilometers on the top and we've got seconds and we've got megaparsecs on the bottom. Now, we've got on the top kilometers, a unit of length, and we've got megaparsecs, a unit of length. So if we can convert Hubble's constant into kilometers per second per kilometer, then we'll have the opportunity to if it's kilometers, so many kilometers per second per kilometer, we've got basically a unit just of per second. The per kilometers will cancel out. Kilometers per kilometer, nothing. No, the number 1 is actually the correct little phrase there. So if you, instead of 8, was it value? I always forget its value. It's supposed to be constant. It's more or less established at 68 now. So if you do 68 kilometers per second per megaparsec, so do 68, and then underneath the number of kilometers in a megaparsec, which is a big number, you will end up with a very, very small number, which has the unit of per second. And what Hubble realized is that if you flip this over, if you invert that number, that very small number, you get a very, very large number with the unit seconds. And Hubble said that's the time for which the universe has been expanding. It's Fergie time, Hubble time it's called, Hubble time. And Hubble had the genius to find, it wasn't just a good experimenter, to find or to suggest strongly that the Hubble time is the time for which the universe has been expanding. In other words, the age of the universe. Fantastic. And it comes out to be about 14 billion years. So that's the length of time for which the universe has been expanding. And cosmology is all to do with, you know, galaxies and the universe at large at the beginning. Will there be an end, or will it go on forever? Was there anything before the Big Bang? You know, suddenly it didn't just happen out of nothing. Well, again, we can't really, even experienced astronomers like myself find it very difficult to think that something just started expanding just like that. Well, we'll look at the evidence of the Big Bang in a moment or two. But it's supposed to be extremely small and very hot and a very dense entity, thing that's been expanding and cooling ever since. And the most accepted theory is the Big Bang theory. It wasn't big and it wasn't a bang. That's a phrase coined by one of the main objectors to this Big Bang theory. The steady state theory proponent was Fred Hoyle, who was also a science fiction writer. So because he wrote science fiction as well, I don't think the scientific world really gave him much credibility. But we'll look at the evidence in a little while. There we go. The main argument still there. Still about 10% of people think that the universe has always been and will continue to do so. Just happens to be expanding at the moment, but it will contract. It's just expanding and contracting over many years, and it just happens to be expanding at the moment. Creates new matter. Don't know quite what the mechanism of that would be, so that the overall density remains constant. Not sure about that. I'm a Big Bang proponent myself. Not keen on the steady state. But some do, 5-10% people, steady state, just like there are 5% of people who believe the earth is flat. The Flat Earth Society, yes. It's got members all over the globe. There's a third model that you might have heard of called the cyclic theory, in which the universe has always been and always will in the future, and it undergoes a series of expansions and contractions. Not too convinced about this either. What's the point? I seem to think. Not sure about the cyclic theory. Not great. Not a great supporter of that. Just a little rider. We are painting a very simple picture of the universe. Please don't go on to Wikipedia and type in cosmology or expansion of the universe. You'll be baffled by all sorts of mathematical symbols and ideas that you've never heard before. So I would suggest you leave that alone. Keep it nice and straightforward for now. And keep it at cosmology for dummies, and we'll all be okay, I think, with that. It is in practice very complex, very mathematical. Yeah, I won't say any more about it. Right, so we've got this little graphic here showing the Big Bang and the cyclic model and the steady state model. So the steady state is expanding at the moment, and more matter is being produced somehow. As I say, I don't know the mechanism of that. I don't think anybody does. And just to keep the density, the overall density, the same. So that's why there are more dots. That's supposed to be lumps of matter. So let's go with the majority, and let's have a look at the further observational evidence for the Big Bang. And this very keen student is wanting to know. The others look like they are going to learn a lot as well. Three main sets of observations. There's what we call the CMB radiation, which is the cosmic microwave background radiation. That's the fact that all over the sky, there are microwaves being detected by microwave receivers. So what you might say, these are microwaves that were once part of the Big Bang. So the supporters say. There are quasars, but there are no quasars nearby us. The quasars that we see are all very, very distant, suggesting that they were formed a long, long time ago. There aren't any quasars now. I'll stick my neck out. There aren't any quasars. All right? We are seeing them because they were created a long, long, long time ago. So the universe must have evolved. There was the kind of epoch at making quasars early on in the universe, and now it's different because we don't have any newly made quasars. We would be able to see them nearby if they were. And also Hubble, in its kind of latter days, in its kind of senior days, it was made to take images of blank, empty areas of sky to see if there happened to be anything there. And astronomers found millions of galaxies. Again, far denser regions of galaxies early on in the universe compared with now. So again, evidence for the fact that the universe has evolved. And that really can only happen with the Big Bang Theory. That map on the left, by the way, is a map of the cosmic background radiation. Small fluctuations in it are the different colors. So it's been very much photoshopped. And that's just a latitude and longitude of the sky. Again, don't go too much into that. I think we've explored the discovery of the microwave background radiation, but here's just a little bit of a reminder. Yeah, a Russian cosmologist called George Gamow, who was very well renowned, said, right, if the Big Bang started off at this temperature and has been expanding for so long, it should now have reached a temperature roughly of 3 Kelvin. And the temperature of this radiation was found to be 2.7 Kelvin. Well, that's an excellent agreement. So, evidence for the hot, dense Big Bang. That's the wrong button again. We're going backwards. We're going cyclic. There we are. Quasars are found only with very high redshifts, so they were present in the early universe, long died out. This suggests the early universe was very different from what we've got today. And there was something very similar in the caption for the Hubble deep field images. There we are. I think you're able to read that. I think that's more or less what I was saying. In the future, we've got various models. This, I think, you will probably need to study in the cosmology section of the text page. Yeah, you've got this on page 69, so don't worry about trying to sketch it now. We've got now, the present, in yellow, at the going sort of across. That's the universe now, as we see it. Now, in the future, it might expand further and collapse. In the future, it might expand and keep on expanding, but at a decelerating rate. It might be what we call a coasting universe, in which it just expands and carries on at the same kind of relative speed. Or, certainly with the evidence of dark energy that I'm not a great fan of, the universe might be accelerating. Again, there is no evidence directly for that. There is no theory as to what is causing it. I like the decelerating universe, which won't actually come to a big crunch in the future. I like the second universe. It's expanding, but at a slowing down rate. That's because I can understand the laws of gravitation to explain that. But as I said, it's not just the laws of gravitation. There's a lot at stake here. There's a lot going on. So in my simplistic wish to understand a little bit about the universe, I'm going for model number 2. And certainly the evidence supports it. And model number 1. And model number 3. I think it's a bit dodgy evidence for the accelerating universe. But many, many, many scientists would disagree with it. Right. Well, we've got some more questions in a moment or two. So from the exams. So let's have. Oh, just a bit there about dark matter. Black holes, failed stars. What are WIMPs? Weak interacting massive particles. Yeah, this dark energy is supposed to be stuff, not the stuff that you and I know, that exerts a repulsive force of gravity. We haven't got any evidence for it sort of in the lab that we can test it. We've no idea what it is, but it's supposed to make up most of the universe. And it's supposed to operate on the largest of scales. Well, I think with the Hubble and the James Webb Space Telescope, we have got to very, very distant galaxies and very, very early universe. Right, so some cosmology questions. Not too many of these because, as I say, they don't really exist very well. Here's one you can have a go at. Little talking Mickeldor out of the way. Which of the following leads support to the Big Bang Theory? So you will get some nice, easy questions on it. CMB radiation, the Hubble deep field, both of these or neither of these? Well, that's a nice, interesting one. I think that's one of mine, actually. I don't think that's from a real paper. A, B, C, or D, gentlemen and ladies, if we have any ladies joining in, maybe later. Have we got anything in the chat, I wonder? Alistair's usually looking out for that.
We've got C that's been offered, so both of these appears to be the suggested answer.
Good, that's the right answer. C, both of them. And the existence of quasars as well. You wouldn't need to justify them, just knowledge and description. This was a funny one. This was about from a couple of years ago. An astronomer states we appear to be living in an expanding universe. Explain what is meant by this statement. We appear to be living in an expanding universe. So there is strong observational evidence that the universe is expanding, that the universe is becoming larger in time. There we go. How's that? I don't need a diagram. We appear to be means it's based on evidence. The examiners are quite keen on that. Observational evidence. To strongly suggest, we appear to be living, strongly suggest that the universe, that the visual universe is getting larger. Okay? It's no good saying the universe is expanding. That's just regurgitating the words in the question. We've got to be a little bit more original. Right. There's the evidence. I think if you wrote, there is strong evidence that all distant galaxies appear to be moving away from us, you'd get your 2 marks. I don't think you need the receiving. Oh, we've got the velocities and distances of some galaxies. Right. That's good. So I think we're asked to plot a graph here. Yeah. Plot a graph. I reckon this is going to come up in every year. This is going to come up this summer, I think. Plotting a graph, determining the Hubble constant and finding the age of the universe. I reckon it's a 50-50, £20 each way. Good return. Velocity in kilometers per second, distance in megaparsecs, and we've got some of the data. And what we've got to do is to add 2 more. So we've not got all the data from the previous table. So let's see what it looks like. There we go. I've added two crosses there showing the data that wasn't there. Lovely line of best fit there, drawn nicely. So if you want to find the gradient, it's rise over run using the gradient, using the line. And we're in kilometers per second per megaparsec. So you would just divide the 68 or whatever value you got by the number of kilometers in a megaparsec, and that would give you 1 over the Hubble time. So you then flip it over, 1 over x it, and there's your answer. Right. Obviously, the data isn't quite as accurate as it should be on this graph because we've not got a value of 68 kilometers per second per megaparsec. It's not even in our range between 74 and 80. I'm not quite sure where they got that from, but maybe they've just given some kind of false made-up data. This is very similar, a bit wordy, but this is very similar to one question we had earlier. An absorption line in the spectrum of two quasars is measured. The observed wavelength, 5.3. Wait a minute, this isn't two quasars. The redshift is much too small. Well, we'll see that in a minute. We'll have a look in a minute. Right, we're going to use the formula twice. Lambda minus lambda naught over lambda naught is V over C. Remember, we had a Z equals earlier, just to tidy things up. So the wavelength is, I'll do the top one, 532.5, take away 520.5, divided by 520.5. Let's just, no, I haven't got my calculator here, it's in the other room. So we can find what the radial velocity is. Then we use the equation to do the same, and we get the two velocities. Right, so don't forget the true wavelength is 520. I'll just get my calculator while you try. Okay, I'm doing the first one. 532.5 nanometers. Take away 520.5 nanometers, which is 12 nanometers. Is that right? Yeah, I could have done that in my head. Right, divided by 520.5, that's the true wavelength. I get a redshift of 0.02. And that, when we multiply by 3 times 10 to the 5 kilometers per second, gives, oh no, we got a recession velocity of 6,920. Right. So we've got one of these galaxies traveling at 6,920 kilometers per second, and the other one at 13,430 meters per second, kilometers per second. So that gives a different, I don't know why they're asking us, excuse me, to do the same thing twice, but I really don't think that those absorption lines in the spectra of galaxies, I don't think those are quasars. The redshift is much too small. Remember, these are very distant objects, very distant active galaxies. Not with redshifts of, what did I say? Point something or other. Was it? Redshift to 0.02. That means they're receding at 2% of the speed of light. Alistair, are you there? Am I making nonsense about this, or am I making common sense? I've been trying not to criticize the examiners, but there we are. I have done in my, well, I think this is the last question.
Sorry, yes,
Quasars don't have redshifts of 0.2, do they? 2% of the speed of light. It's more like 30, 40, 50, 60, 70% of the speed of light.
That's what I would have thought. Yes.
Yeah, that's another thing to query on last year's paper. And another question, a nice multiple choice for you if you want to. You can shout your answer out if you like, ladies and gentlemen. Which pair of quantities are related by Hubble's law? Nice easy one. Put it in chat
Go
or
on, guys.
shout your answer out.
We've had C offered.
We've got C offered. B.
Oh, it's a B.
Wavelength doesn't come into it. So the recession velocity is equal to the Hubble constant times distance. Good. Any questions? Please just put them in the chat. I don't know whether we've got many questions, but the chat seems to be more like hello, yes, and thank you recently. So that's absolutely fine. So thanks for joining us tonight, this afternoon, whatever, in the last revision webinar. And as Alistair said earlier, next time it's going to be a kind of, ask the examiners, ask an astronomer. So revision, things that you'd like us to go through.
Oh,
and,
hold on. Sorry, Nigel, we've just got a request through. Could we have a look at the Hubble constant graph question again, please?
Can we look at the Hubble question again?
Yeah.
Yeah. The graph one.
That's what he's asking for. Yeah. I'll stop the recording now.
Okay.
You've been through all the... That way people can... There we are.